Let's look at final exam question number 88, found on page 679 of Teach Yourself Electricity and Electronics 5th edition. The question talks about a series RLC circuit. R stands for resistance, L stands for inductance, C stands for capacitance. So this is a series resistance, inductance, capacitance circuit. We test it with a, well, there's various ways to do that, an impedance bridge and other types of specialty circuits. We test it. There's another thing called a gate dip meter, a grid dip meter. Those are topics sort of off to the side of this discussion, but we can use any of them to test a circuit like this. Suppose that we test it and we find that the resonant frequency is 30 megahertz. And we know that this particular resistor is 10 ohms. It's easy enough to check that out with an ohm meter. We don't necessarily have to know what these component values are. All we know is that the resonant frequency is 30 megahertz. If we change that resistance to 40 ohms, what's going to happen to this resonant frequency? Is it going to go up? Is it going to go down? Is it going to stay the same? The answer is that it's going to stay the same because the resonant frequency of this type of a circuit depends only on the inductance and the capacitance. It doesn't depend on the resistance. However, that said, the characteristics of the circuit will nevertheless change anyway, and here's how. So, getting back here, the correct choice is C as in Charlie, 30 megahertz. It'll be the same 30 megahertz with the 40 ohm resistor as it was with the 10 ohm resistor. But let's suppose that we apply a signal to that circuit. At one end is the input, the other end is the output. We plot frequency on the horizontal axis, and we plot sensitivity or signal strength on the vertical axis. We apply a signal to that circuit at one end and see what we get at the other end. The resonant frequency is 30 megahertz right here. With the 10 ohm resistor, we might see a frequency response something like this. The circuit will not pass very much signal energy until we get very close to the resonant frequency, and of course the best signal passage through the circuit will occur at the resonant frequency. Now we change the resistance to 40 ohms. We're going to see that it's still resonant at 30 megahertz, but it's a lot shallower of a response. At the resonant frequency, it won't pass quite as much signal because there's more resistance in there that creates more loss. This is with the 40 ohm resistor, as compared with the 10 ohm resistor. So, we're going to see a shallower response. The circuit will, in fact, I think, it's hard to say exactly what it's going to do down here. I think actually the whole curve will be down further. Sort of look. Well, I'm having a little bit of trouble here, but I'm just going to keep right on going. Trouble picking the right colors. The blue represents the 10 ohm resistor, and the green represents the 40 ohm resistor. In any case, we're going to see a different kind of behavior in the circuit, and in order to actually know for sure what these curves exactly look like, we'd have to test them and graph them on a specialty instrument for that purpose. A spectrum analyzer and a sweep generator will do that. But we'll notice that the 10 ohm resistor produces a sharper peak and a higher peak than the 40 ohm resistor does, even though the resonant frequency remains the same. Just a little bit of a, I like to give you some extra information in these explanations, hoping that you'll learn something a little extra, and maybe I'll learn what color markers to use. Again, the correct choice in this case is C, as in Charlie.